Good morning. I'm absolutely delighted to have been invited to speak to you about the HamSCI, that's the approved pronunciation, Personal Space Weather Station. Now, this list of co-authors gives you some impression of just how many contributors there are to this HamSCI project, and others will appear on individual slides. So today I will cover the development, the deployment, and data from personal space weather stations, which I will abbreviate to PSWS. So what is a PSWS? It's a set of up to 4 modules, a multi-instrument, ground-based system to observe the ionosphere and the Earth's geomagnetic field. Each installation provides valuable information in its own right while contributing to a distributed network of such stations. The components are deliberately low cost while still delivering precise data usable for science. Each component is buildable or deployable by professionals, schools, and of course radio amateurs. The simplest PSWS is one instrument out of this set of 4. A HF receiver augmented with a GPS-disciplined oscillator and able to measure the time of flight of signals. A ground magnetometer to measure the Earth's geomagnetic field. A specialized receiver and antenna for VLF frequencies below 15 kHz, and a multiband whisper transmitter, the WSPRsonde. So a PSWS is designed to provide information to answer questions, be they from the amateur community or the professional research community. And I've listed some topical questions here. And let me take you through one example using these 2 graphs. So on the left is the difference in frequency between the known frequency of whisper transmitter WW0 WWV at Fort Collins, Colorado in the USA, and the frequencies reported by 7 different stations across the USA at 14 megahertz. Now, except for W0 DAS, which is just 7 kilometers from the transmitter and heads ground wave, and these black dots with no frequency change, all the other stations show a pattern of a frequency difference that started with positive values, large positive values, 2 Hertz, decreasing, going through 0 and ending up negative. And that happened over about a period of an hour. That happened during the night. So why did 14 megahertz reopen after it had closed during the night? So that's a question that a radio amateur might figure out. Some might say perhaps it was sporadic E. Well, no, because it occurred over the entire continent of North America, and maybe at slightly different times. So why did it happen? Let's turn to some science on the right. Now here we have Doppler shift, the frequency difference between transmitter and receiver, again on the y-axis. And this time the transmitter is WWV, also at Fort Collins, Colorado. And here, instead of whisper Doppler shifts, we have a Doppler spectrogram from a personal space weather station out due to an 8GA in Ohio, and this is an 1820 kilometer path on 10 megahertz. And we can see a multitude of frequencies, of Doppler shifts here due to different propagation modes. And I've highlighted some of them. The darker trace here is 1 hop via the F region. There's a trace that's weaker and with a greater Doppler shift due to 2 hop via the F region. There's a thin line with near 0 Doppler shift, and that's from propagation via the E region, and then a step here. But what do we have here? We have the emergence of just after 0400 UTC, the band open for 2 hop F2 great circle propagation, starting with a positive Doppler shift, going through 0 and going negative. So that event, 10 megahertz opened for 2 hop propagation with the same Doppler signal as our whisper spots observed by radio amateurs. So there was something coherent going on here. And what that personal space weather station Dopplergram told us was that the periodic variations, this particular period with a flat top, caused the band to reopen. A traveling ionospheric disturbance, which was wafting the height of reflection up and down, hence the Doppler shift, also squashed the reflecting region. It increased the electron density, increasing the maximum usable frequency, and thereby opening 14 megahertz on the path. And so this is a nice example of a question from amateur observations and a science explanation from a personal space weather station. Now, of course, professional ionospheric research instruments have their place. But just look at this map of the coverage over 24 hours from a single component of a personal space weather station, a WSPRsonde transmitter, which operates on 7 bands with 1 watt output on each band, and that happens simultaneously. And this is operated by John, TI4JWC, in Costa Rica. And it really does provide dense coverage to North America and to Europe. The lack of whisper receivers in South America and Africa is understandable, but I should stress, and throughout this talk really, there is much help available within the HamSCI community, both the professionals through their research funding and through fellow amateurs, to install equipment in out-of-the-way places, or places that are underrepresented with the current installations. And we'll see in a later example is a UK amateur providing a WSPRsonde transmitter, just like this one here, for an operator on St. Helena. And perhaps through AMSAT SA and your connections, we can encourage whisper reception and reporting in South Africa. So having seen the coverage of a single WSPRsonde transmitter and making use of amateur receivers, what about HamSCI personal space weather station receivers? What's their current spatial density? Well, here's the current status. There is fair coverage in the United States, a few stations in Canada, a small handful in Europe, 2 in Australasia, and, notwithstanding technical issues from time to time, 1 station in the Arctic, that's VY0 ERC, and at the Germany's Antarctic station von Neumayer, not too far from the Sanai base, we have DP0 GVN. And a recent grant to the University of Scranton that leads HamSCI means that it will be deploying another 20 receivers in the coming months and 10 WSPRsonde transmitters. And again, let me say, if there is interest through AMSAT SA in hosting a PSWS receiver, it could be worthwhile contacting the HamSCI lead, Dr. Nathaniel Frizzell, to discuss. So let's move on to some hardware. These are the original HamSCI receivers. They were known as GRAPES, standing for the Great Radio Amateur Propagation Experiment. GRAPE 1's a home-built, single-channel, direct conversion design with a GPS-disciplined oscillator. GRAPE 2's are 3-channel versions. Now, many of these original grapes still return data daily. A current variant, the through-hole grape by Bob W1XP, recognizes that a simple design that can be built from scratch by amateurs is valuable as an introduction to construction, whilst also contributing to a scientific network. So that's another option to consider, one of these grapes and a through-hole grape in particular. But today, the recommended receiver goes by the name HFRx, and we'll see what it comprises on the next slide. But in brief, it can receive simultaneously hundreds of signals on any set of frequencies between 100 kilohertz and 60 megahertz. Each frequency will be accurate to better than 1 millihertz. Where it is possible, for example, using the time ticks from WWV, and it can give a time of arrival to better than 1 microsecond. So this unattended HFRx can, again simultaneously, monitor time-standard transmissions such as from WWV, a host of amateur protocols, including the WSJTX mode, Whisper, FT8, MSK144, and specialized transmissions such as Oscar Ocean Surface Radar and HF Data Link aeronautical operational control messages. And at what cost? Well, $700 for an entry-level system and $1,500 for the full science-grade installation. Here's a block diagram of an HFRx. Starting on the top left with a broadband antenna, the example of an antenna in several stations is from the company DX Engineering as an active vertical, but many radio amateurs have their own favorite broadband antenna. Next, we have an anti-aliasing filter, and in a full science system, we have the TS1. This is the time sync injector that I'll describe in a moment, and this is used for measurements of time of flight. Next is the heart of the HFRx, an RX888 Mark II software-defined radio, or SDR, connected over a USB 3 link to a host Linux computer that runs specially developed software that I'll outline. The TCXO in the RX888 is fine for reporting multiband Whisper and FT8 spots, but for scientific measurements, we add, here in the orange box, a GPS-disciplined oscillator, usually one from the UK company Leo Bodnar Electronics. And finally, a connection to the internet is needed for reporting. So here's the heart of the system, the RX888. This really is the enabling component. So it was realized by my fellow author and longtime collaborator, Rob Robin at AI6VN, that this SDR, bare bones, with its raw 16-bit ADC output, rather than pre-processed through an internal FPGA, could be used with, at that time, a little-known software package from Phil Kahn, KA9Q. The result would be a receiver that could provide hundreds of simultaneous channels for about $650 when used with a modest Linux mini PC. Now, the downside from the RX888 is that it comes from unknown manufacturers in China. Quality can be variable, and there are poor clones and scams around various internet sites. Now, obtaining a frequency accuracy of better than 1 millihertz, which is required for scientific purposes, is quite straightforward with the GPSDO. Just pass a 27 megahertz reference from the Bodnar through to the RX888 via an adapter, which is really an attenuator. Time stamping is more complicated. Now, within the TimeSync 1 box from Turn Island Systems, we have these blocks within this diagram. There is a GPS receiver with a 1 pulse per second output that flips the phase of an 84.225 megahertz signal out of the synthesizer. And this 84 megahertz signal is injected into the antenna path at about S9. And that marker signal, with its precise times of phase change, goes through exactly the same signal processing path as the signals to be timed. And then it is up to software to determine the time difference for maximum correlation between the internal BSK signal and the signal of interest to determine the time of flight of that signal of interest. So let's dive a little deeper into how the HFRx can receive hundreds of signals simultaneously. It's because of Phil Kahn's KA9Q radio. So in this simplified diagram, 16-bit IQ data at 64.8 megasamples per second, and you can run the receiver at double that, 129.6 megasamples per second. But all of that data goes over USB 3 into your host PC. Every 20 milliseconds, there's a block of data comprising 80% new and 20% old, so we have overlap. And Phil Kahn's code performs an FFT of these 1.62 million samples once every 20 milliseconds. And recall that then provides us the entire spectrum from 0 to 32 or 0 to 64 megahertz. It's as if we were generating a full spectrum waterfall every 20 milliseconds. That's the way I like to think of it. And then for each frequency of interest, we have a digital passband filter with their frequency, center frequency and widths to suit the modes. And we extract the relevant bins from the FFT, and each of those passband filtered data sets gets converted back to the time domain by an inverse FFT, and the result is then a WAV file for each frequency and mode of interest. Now, Phil's estimate is that processing one frequency takes 0.7% of one core of a modest PC. So you can see if you have 6 cores and you only need 0.7% for a frequency, that's how you can have hundreds of channels. But then, of course, we have the question, what do you do with the WAV files? So again, we turn to the work of Rob Robinett. Rob, who had thought to use K9Q in the first place, already had the answer to processing the WAV files. His Whisper Daemon software package already handled multiple WAV files from Whisper and FST4W signals from Kiwi SDRs. And it was relatively straightforward for Rob to add decoders for Whisper, FT4 and FT8, and to convert time standard station WAV files into the digital RF format to incorporate into his release 3 of Whisper Daemon. And here, of course, he draws on help from other radio amateurs, Franco K4VZ in particular, and much of the software for handling the digital RF format was developed at the MIT's Haystack Radio Astronomy Observatory. That's an outline then of the full path from antenna to data into databases in HamSCI and WhisperNet, PSK Reporter, as well as HamSCI's own network, which is PSWS network.caps.ua.edu, and that's at the University of Alabama. So in development by Rob and a series of collaborators is the next generation system to process WAV files. Known as SIGMOND, for Signal Monitoring Daemon, Rob, especially with Michael AZ0G, they're at about the alpha test stage. And apologies for the type that's too small, it's just a consequence of how much functionality is in SIGMOND. So as well as performing all of the tasks that Whisper Daemon, as we saw in the last slide, it adds in processing for time of flight, data acquisition and processing for a magnetometer, and for other types of signals you can write any decoder for. And decoders for signals from the CODAR ocean surface current radar and the HF data links for airborne comms are under active development, each reporting to already existing or new databases. A key feature of SIGMOND is its ease of configuration and installation. And I should mention that much of the code has been drafted, should I say, by Anthropic's Claude AI with much review and debugging by humans involved in the project. Now, before I leave the HFRx, there's one more very useful feature. A web interface with all of the usual features that you'd expect of a web SDR. They are available to you directly at the console or via the internet while the system is performing all of those processing tasks that I've already described. That is Whisper, FT8, WWV, and reporting all of those. You've also got it available to you as a web SDR. And this is from my friend G4HZX in London on his vertical antenna. And I can access his SDR as well as other people could over the internet from here in Southampton in the UK. So tremendous capability for $700. Let me move on to the second and optional component of a PSWS, and that is the ground magnetometer. The measurement is made by a 3-axis magnetoinductive sensor. HamSCI members have designed a breakout and communications board that fits in a plastic pipe placed in a hole so that it minimizes drifting due to offsets in temperature changes. The magnetometer connects directly to a computer. As we can see, it can be the same as for the HFRx, and cost of the magnetometer is about $100 to $150. It does need to be well away from mains wiring and ferrous objects that change their positions, such as cars or garden machinery. The map on the left shows why HamSCI is very keen to deploy amateur magnetometers across North America. The official government network, maintained by the US Geological Survey, is very sparse. There are only 6 sites in the lower 48 states. Contrast that with the excellent coverage in Finland, 11 magnetometers in a country 1/30th the size. And more sites matter because the variations induced by a geomagnetic storm are on scales as small as a few hundred kilometers. A sparse network aliases those variations, leading to distorted maps of ionospheric currents. So let's move on to reading the HamSCI magnetometer. How do you find the HamSCI magnetometer data? Well, go to this link on HamSCI's PSWS database, and from a selector list you can choose magnetometer and a date interval. Select a particular site, and it's one click to download a CSV file for the previous generation instrument or a JSON file for the current generation. And here I've plotted the magnetic anomaly for the horizontal component of the Earth's magnetic field at amateur site N5 VRG Texas in orange, and the US Geological Survey instrument in Boulder, Colorado, some 1,080 kilometers distant in cyan. Now, by magnetic anomaly, I mean the difference between the reading at any particular time and the average for the whole day. And we do that because the variations here, typical of a quiet day away from the auroral regions, the variation is about 30 nanotesla. The Earth's total field is about 50,000 nanotesla. So we're looking for about a 0.1% change. And that's why we calculate and plot the anomaly. And I think you'll agree that despite having an offset of less than 10 nanotesla and small differences from being 1,000 kilometers apart, which is what we're interested in, this is generally a very good comparison between the amateur magnetometer and that from USGS. You will notice some small scale noise, short period noise variations on the amateur magnetometer that you don't see on the professional. But it's a good instrument for $100 to $150. The third component is a specialized receiver for VLF, for 15 kilohertz or below, developed by HamSCI member Jonathan Rizzo, KC3EEY, shown here alongside his active antenna. Jonathan's hardware and software designs are open source. He aims to capture natural signals known as whistlers and dawn chorus. These intriguing signals you've just heard are generated by lightning in the troposphere. Some of the VLF component escapes through the ionosphere, after which the signals propagate along magnetic field lines in the Earth's magnetosphere, which can be out to a few tens of kilometers before re-entering the ionosphere in the opposite hemisphere and reaching ground. The active antenna comprises an E-field monopole with a high-impedance preamp far right, and both parts are housed in a plastic pipe as in the previous slide. The VLF signals are digitized by a 24-bit audio ADC with a GNSS timestamp from an interface box designed with Paul Elliott's WB6CXC. And data processing is via modules in the extensive toolbox VLF-RX tools written by the late Paul Nicholson, G8 LMD. Now, the sighting requirements for a VLF receiver are much the same as for a ground magnetometer. Ideally, 60 meters or more from wiring carrying mains harmonics, at least 10 meters from overhanging branches, and ideally in open ground. However, Jonathan and colleagues recognize that compromises are inevitable at many potential amateur sites, and it's best to discuss options with him if you're interested in VLF. So to round off, here is a spectrogram with frequency from 0 to 16 kHz on the y-axis and just 6 seconds in time on the x-axis, and just faint but visible is this decreasing frequency. That's a downward sloping Whistler. You can just make it out between crashes here due to local sources. The fourth component of a PSWS is the WSPRsonde multiband transmitter. Again designed by Paul, WB6CXC, the WSPRsonde transmits WSPR simultaneously on up to 8 bands, selected between 160 and 6 meters. Each frequency has 1 watt output, and up to 6 outputs can be fed to a filter combiner to output to a single multiband antenna. Examples in use include multiband trapped verticals, fan dipoles, and end-fed antennas, and 2 frequencies of separate output, for example 160 or 6 meters. There are a handful of WSPRsondes in operation, with 10 in stock about to be sent to volunteer hosts. The WSPRsonde is available from Turn Island Systems at about $650 and $160 for a 6-band filter combiner. Now, a key advantage of the WSPRsonde is that its transmission frequency is precisely known, which means that when decoded by receivers with GPSDOs, such as the HamSCI Grapes or HFRx, the difference between the transmission frequency and the measured receive frequency is the Doppler shift induced by the ionosphere. And in that regard, a WSPRsonde can be thought of as a very low power WWV. And indeed, one WSPRsonde is sited on the WWV estate. Here are plots of frequency shift in green in the top diagram from -1 to +2 Hertz, and in the bottom panel, signal level on dBm from -140 to -100, and these plots are in yellow. And this is for a path from John, TI4JWC in Costa Rica, to an HFRx AC0 in Missouri, USA, on the 10 megahertz band. And you can see that there were small variations in Doppler shift before dawn, but then with a clear rise at dawn, followed by some periodic variations. And the clear rise is as the reflection height from the F2 region descended as the sun rose. And so we get good quality Doppler data from a WSPRsonde on several bands simultaneously. Let me now move on to some typical deployments. So here is a typical HamSCI PSWS home station comprising just the RX888. And it's a simple tabletop installation at K3LR, Western Pennsylvania. Now, to replicate this setup, as well as the equipment I've described earlier, I'd strongly advise reading the PSWS overview page on the HamSCI website and the guide to setting up WSPR-Daemon. You'll need a broadband antenna, and you may already have a personal favorite that will be fine. Or you may want to look at an active vertical or an active loop. You'll need an internet connection to report the data. And if reporting all WSPR FT8 bands and the time standard stations, the guide is about 80 megabytes per day. If you might be interested in a remote HFRx, here is one I maintain on behalf of the Radio Society of Great Britain's Propagation Studies Committee. Reporting as GB0 PSC, the RX888 with a Bodnar GPSDO, a timesync injector, and a B-Link mini PC with pre-installed wiring, they're all on this wooden baseboard screwed to the wall of this wooden hut out in a field at Baldock, UK. And that meant that I could thoroughly test it entirely at home, leave it exactly as it was, and transport it to the remote site for a trouble-free installation and operation. And this is at Baldock, which is the National Spectrum Monitoring Centre of Ofcom, the UK equivalent of your ICASA. I use a standalone 4G wireless router to be completely independent of the Ofcom network. Now, HamSCI is fortunate to have members that enable reception or transmission at out-of-the-way places. Pierre V3KTB has installed a HFRx at the Pearl Laboratory, Eureka in Nunavut, reporting as VY0ERC. At 80 degrees north, the site is about 260 kilometers from the geomagnetic pole, and so shows some of the wildest swings in Doppler shift I've noticed. In contrast, here is DP0GVN at Germany's Neumeier station at nearly 71 degrees south, well away from the geomagnetic south pole, and on quiet days it's indeed north of that auroral oval. And this has been installed with support from DARC, Germany's National Society for Amateur Radio. The WSPRsonde is working well, but the HFRx currently has a problem. Now, the WSPRsonde installation on St. Helena is interesting. It's hosted by Gary, ZD7GWM, with the equipment provided by Dr. Jerry Bolger, G3WIP, and Turn Island Systems. Jerry does have an HFRx, but has yet to find a location and operator for it. So we're now on to my third section on data and science. All HamSCI PSWS data is open for all to access and use. A reminder, here is the URL of the central control system, your gateway to the data. This Observations tab is where you select a data set of interest from a combination of instrument on the left, station nickname, and times. And a simple click on the list of files will bring you up automatically a Doppler spectrogram, Doppler on the y-axis, time of day 24 hours on the x. And here is 2.5 megahertz to the Baldock station. There's also a simple line plot of the signal level. And in this way, you can browse data without doing any processing. But if a plot is of interest to you, you can download the plot or the raw data to do some more processing. But what indeed do these spectrograms show? That was a question asked by HamSCI member Bob, N6RFM, and he came up with the idea of a compendium, an atlas of Doppler spectrograms, showing and describing different propagation features and a range of events. It's freely available on this Read the Docs page. And here's an example on the right. And this is an underappreciated propagation mode, not along the Great Circle path, occurs above the normal MUF, and that is 2-hop side scatter, where there is no direct signal, but where two circles intersecting, the circles centered on transmitter and receiver, at the intersection, signals can land from the transmitter and be scattered back to the receiver. Hence signals they're much weaker, but propagation is possible. And that's what's happening during this time, shown by this example of a Doppler spectrogram. There are many other quirky examples on this document. HamSCI coordinated a series of propagation experiments during the 2023 annular eclipse and 2024 total eclipse, prominent over North America. And here are Doppler spectrograms of WWV at 3 frequencies received by Nathaniel Frizzell in Pennsylvania. And this dot dash curve is the sun's altitude, and the dotted curve here is the obscuration due to the eclipse. And you can see this 20 megahertz Doppler shift goes negative as the moon covers the sun, goes through 0, and then as the sun becomes less obscured, then the Doppler shift is positive and then returns to 0 again. and this pattern is repeated in different forms on other frequencies. And the solid line is a computer model of the eclipse. It has a little way to go to be an accurate representation. I should have said that at each of these science examples could be a talk in itself, and that's the case here. These are measurements of the time of flight from WWV to KA7OEI, the Northern Utah SDR site. We're on 20 megahertz on this 670 kilometer path. We're above the MUF, with the receiver well within the skip zone, and yet we have a WWV signal over these 18 hours. Normally, we just have the signal level lower panel to give some information about what might be going on. And this would have given me, used to these data sets, clues for periods A, C, and B. But I have no idea what other propagation modes would have been going on. The time of flight gives me the extra clues needed to come up with the suggested modes on the right. I'll start with mode C, stronger signal, the well-known mode sporadic E, along the great circle with a time of flight of just over 2 milliseconds. Modes A, B, and H were the same, 2-hop side scatter, the same mode as we saw on the spectrogram. In A, what's happening is that the distance increases in the evening as those circles that I described grow in radius, and in the morning, those large diameter circles become smaller in diameter as the morning and the sun rises. That's what's happening there. It briefly reappears at H. The other modes were new to me. E is 2-hop side scatter, but not via the F region, via the sporadic E that had been present in C, but had moved away from the great circle path. That was 8 milliseconds travel time. Mode F is forward scatter, very weak along the great circle. And mode G, with a time of flight of about 12 milliseconds, is a well-known mode at VHF, auroral backscatter, half-hop ionospheric backscatter. So this is how time of flight really does help to add detail. Here's an example of Doppler spectrogram and PSWS during a solar flare from the 10th of May this year. Top left is the flare and the spectrogram of the response. Well, immediately what we see is a radio blackout during this period, the well-known effect of a solar flare increasing absorption in the D region. But you can just make out a very faint line nearly vertically up, the so-called Doppler flash that's associated with it. What we have here is the path from CHU Canada to GB0 PSC in the UK. But we can now look in more detail than the spectrogram. On the left is signal-to-noise rate, signal plus noise level in blue, noting that I've reversed the right-hand axis for X-rays, which I've plotted on top in orange, so we have small to large, the inverse axis on the right-hand side, and we can see that the reduction in signal plus noise level in blue really follows quite closely the increase in the X-ray emission from the sun with a bit of a lag. That's fairly well known. What was really quite a surprise was the Doppler shift on the y-axis, and in cyan is the Doppler shift calculated every 3 seconds from the Personal Space Weather Station. And then in a dark green we have the rate of change of ultraviolet radiation from the sun, how quickly the ultraviolet radiation is changing, it's fluctuating. And for each pulsation in the ultraviolet, here, here, and here, there is a change to the Doppler shift a few seconds later. And that's really quite an interesting finding from the Personal Space Weather Station. And my example for a HamSCI for a geomagnetic storm comes from a magnetometer on the left and the Doppler spectrograms from the receiver on the right, although not at the same site. And it highlights the difficulty of finding a good magnetometer site. On the left, we have the horizontal magnetic field anomaly and a large step as the shock wave arrives. What we see in the Doppler spectrogram at the time of the shock wave is some small disturbance on both frequencies, but really that's the ionospheric disturbance happens some hours later. The wild swings in the Doppler, and in fact they swing more than 5 Hz out of range on the path for, at 14.67 megahertz. Those shifts were delayed compared to the shock wave. Oops. So let's have a look at it, and I'm going to skip that slide, but look at the advantages of a WSPRsonde. With its 1 watt transmissions every cycle on multiple frequencies, WSPRsonde is a brilliant tool for studying short-lived transequatorial propagation events. So in this example, from DP0 GVN Antarctica to the Canary Islands, we have 21 megahertz in orange, 24 in cyan, and 28 in magenta as the WSPR signal-to-noise ratio. And you can see that 28 megahertz opened up with a phenomenal SNR of plus 13 dB on this path for a few minutes. A short-lived event, so it was important to get data every 2 minutes. And it was important to get data at the 3 frequencies, because that real rise in signal level was only on 28 megahertz, a smaller rise on 24, and hardly any change at 21 megahertz. And we see measure Doppler shift as well on each of those paths. And doing a ray tracing, if you can see it, then why I think that the signal-to-noise ratio went up so high to plus 13 was that we had just 2 hop signals. We had this ray here, which was ducted for almost 5,000 kilometers, and then the second hop was into the ionosphere, and then it does not touch ground here, but continues, and then is refracted back in the ionosphere to EA8 BAK. So some interesting propagation studies from the multi-frequency simultaneous WSPRsonde. And I should say that, of course, much of the science that comes out of the PSWS is published. Here is an example in the open source literature from this year. As I get towards a close, here's some glimpses of some major projects underway. Here is a potential replacement for the RX 888, the TAPA RX 888, that is truly open source, known manufacturer, and this is now at the stage of testing prototype boards constructed or built in China. And you'll find that HamSCI is trying to migrate its code into a single repository and working on time-referenced beacons for WSPR and FST4W. So my last slide is to encourage you to first join the HamSCI community. A single click at HamSCI Get Involved will do that. Get to know the community. It's very friendly. There's over 1,500 people signed up. If you feel like starting with a single component, build one. Come and join the network. Look at all the resources that are available and join the Google groups that HamSCI has for discussions on its various topics. So thank you very much indeed for your attention today. It's been a pleasure to talk with you.